All right, let's talk about L'Hopital's rule. Now, as I wrote in the introduction to this section, L'Hopital's rule is another method for evaluating limits, and we use it when we have limits that are of the form 0 over 0 or plus or minus infinity over plus or minus infinity. And those are two indeterminate forms, and we can apply L'Hopital's rule when we have those two specific situations. Now, if we have other indeterminate forms, we'll talk later in the lesson about how to manipulate those limits so that they become 0 over 0 or plus or minus infinity over plus or minus infinity, and then we can apply L'Hopital's rule. Now, I have to say that I love L'Hopital's rule, and I remember it very vividly from when I took calculus, and it's just a lot of fun. So I've written up here both forms of L'Hopital's rule, the first form and the stronger form. And we're going to talk about them separately and how they really work together. So theorem 4 says, suppose that f of a and g of a are both equal to 0, and that f prime of a and g prime of a exist, and that g prime of a isn't equal to 0. Then, in the limit that x goes to a, f of x over g of x is equal to f prime of a over g prime of a. Now, how did we get here? You might want to ask yourself. Well, if we took the limit as x goes to a of f of x over g of x, and we just substitute it in, which is one of our ways of evaluating limits, then we would have f of a over g of a, and that would give us 0 over 0. And that is that indeterminate form. Now, we're going to talk in a couple of minutes about how we got this. But what if, when we substitute in, we still get an indeterminate form? Well, then we're going to want to apply L'Hopital's rule again, which gives us the stronger form down here in theorem 5, which says, suppose again that f of a and g of a are equal to 0. But now we have to say that f and g are differentiable on an open interval containing a, so that just means in the area around a where our limit is headed. And that again, g prime of x isn't equal to 0 on I as long as x isn't equal to a. Then we have this stronger form down here, which says the limit as x goes to a of f of x over g of x is equal to the limit as x goes to a of f prime of x over g prime of x, if the latter limit exists. And that's really where we get into that situation of maybe this is going to be equal to 0 over 0, or plus or minus infinity over plus or minus infinity. And because of the way the stronger form is set up, it allows us to apply L'Hopital's rule again because we're taking the limit again. So we're actually going to go through the math, kind of a, not really a proof, but more of an explanation for the stronger form. And we'll take a little side trip to see where that first form comes from. So let's let h of x be equal to f of x over g of x. And we are going to assume that f and g are differentiable around some point a. We're going to assume that f of a and g of a are both equal to 0. We're going to assume that g prime of x is not going to be equal to 0 as long as x isn't equal to a. Basically all of the conditions that we had in the two theorems. So what I really want, of course, is to take the limit as x goes to a of h of x. So I'm going to substitute in for what h of x is. So I have my limit as x goes to a of f of x over g of x. And by the property of limits, I can divide these out and say that I've got the limit as x goes to a of f of x, and that's going to be divided by the limit as x goes to a of g of x. And if I substitute in for the limit, I'm going to have f of a over g of a, which is going to give me 0 over 0. Well, this is the indeterminate form. It does not give me an answer to my limit. So I'm going to have to do something different. And I'm going to have to back up in my algebra here and see if there's a way that I can resolve this or change this. So let's go down here. And I'm going to start again with h of x is going to be equal to f of x over g of x. And then basically I'm going to subtract 0 from the numerator and the denominator. So I'm going to have f of x minus f of a divided by g of x minus g of a. Now I can do that because f of a and g of a are equal to 0. That was one of our assumptions up there. All right, so far, no problem. Now I want to divide the numerator and the denominator separately by x minus a. So this is going to become f of x minus f of a all over x minus a divided by g of x minus g of a all over x minus a. Now, I'm really interested in the limit as x goes to a, so I'm going to take the limit of both sides. So I'm going to have the limit as x goes to a of h of x, and that's going to be equal to, and I'm going to take the limit separately in the numerator and the denominator. So I just rewrite what I have up here, divided by the limit as x goes to a of g of x minus g of a all over x minus a. Now this should look familiar. What is the numerator? What is it? Think back, chapter 3, what is that? Well, that numerator is in fact f prime of a. And the denominator is g prime of a. And this brings us to the first form of L'Hopital's rule, theorem 4. And that's good. That's okay. So this is theorem 4. But what if for some reason I get another indeterminate form? What if this turns out to be infinity over infinity? Then I haven't really helped myself. So I need to back up for a minute and write this a little bit differently. So because f of x and g of x are continuous, because they're differentiable, at least near a, I can really write these derivatives as the limit as x goes to a of f prime of x divided by the limit as x goes to a of g prime of x. And of course, using my properties of limits, I can say that this is the limit as x goes to a of f prime of x divided by g prime of x, which is in fact the stronger form of L'Hopital's rule. It's theorem 5, and because I have this limit here, if I end up with infinity over infinity, then I can apply L'Hopital's rule again. And you could probably see a situation where I might have a high-order polynomial in the numerator or the denominator, and I'm going to need to keep taking derivative after derivative after derivative until I can get a constant so that I don't have 0 over 0 or plus or minus infinity over plus or minus infinity. Now, I'm going to say this many, many times, but you need to remember that you have to take the derivative of the numerator as its own piece, and then you take the derivative of the denominator as its own piece. We're not going to be using the quotient rule in any way. We're taking the derivatives separately. So this is an introduction to L'Hopital's rule, and we will do several examples to help you walk through the steps and become more comfortable with it.